with our remaining time. Let's make a formula sheet, and then we're going to work a few problems, okay? So the first formula I introduced in chapter 2 was that the speed of light equals the wavelength times the frequency. Anytime you plug in wavelength or frequency in any of these equations, wavelength needs to be in meters so that all our units cancel appropriately, and then frequency needs to be in inverse second. Yes. And 1 inverse second is equivalent to 1 hertz also. Okay, so this equation we can rearrange and solve for either wavelength or frequency, depending on what the problem asks. We always know C is a constant. It's the speed of light. And any constants, I'll give you on your test. So C is the speed of light. All right. The next equation that I introduced was the energy equation in terms of frequency. So it's H, which is Planck's constant, times frequency. So the H, again, is a constant, so I'll give you that. All right, so anytime you use this equation, that is the energy of a single photon in joules. I say that because if you've looked at some of the book problems or even some of the ones I crossed out, it'll say what's the energy for a mole of photons. Well, that's not how you do it then. This is for a single photon. All right, we could rewrite this equation in terms of wavelength. Basically, I rearranged this part and then substituted in for my frequency, but you don't have to know that, just remember this. So HC, both are constants, over wavelength, which is in amperes. Again, these two equations are the same, they describe the same thing. It's just, did I give you frequency or did I give you wavelength? And the last one I covered was the de Broglie wavelength. Anytime you are to use this equation, it will mention de Broglie in the problem. We'll either say calculate the de Broglie wavelength or the de Broglie wavelength is, and you find something else. So for the de Broglie wavelength, on the bottom, we have mass, which needs to be in kilograms, and then U, which is velocity, and it needs to be in meter per second. And again, if you just remember that these two need to be in those units, then anytime you plug it into this equation, you'll get meters as your wavelength. And you don't have to do that 1 joule equals 1 kilogram, yada, 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 that I did in my recording. All right, so that's all I've done so far in chapter 2. So let's look at an example. I'm pulling these from a different book just so that you have plenty of practice problems to do on your own in your book. What's the wavelength? Okay, so what is the wavelength, and then what's the wavelength in nanometers of light having a frequency of 1.9 times 10 to the 13 hertz? So we're given frequency, asked to find wavelength. So we're going to use the speed of light equation. C equals lambda times frequency. I'm solving for wavelength, so I'm going to rearrange this equation. I'm just going to divide both sides by the frequency so that it cancels. So it's wavelength equals C over frequency. Remember, hertz, same as inverse seconds. So you don't have to change anything there. Just plug in your numbers. Be sure to type this in your calculator and make sure that you're getting what I'm getting so that we know that we're taking care of these exponents correctly. All right, so when I plugged in my numbers, I got 1.58 times 10 to the negative fifth. If I look at units, this second cancels this inverse second, so I'm just left with meter, which is good. That's a wavelength. Yes.
So for when you solve using the speed of light on the first equation, wavelengths in meters, but when you solve for energy, it's in nanometers?
No, it's in meters as well. All of these equations, it has to be in meters. That's where they always throw you the conversion. They're going to either ask you to find wavelength and then you have to convert it to nanometers, or they're going to give you wavelength in nanometers. You have to convert it to meters. All right, so let's take this number now, convert it to nanometers. Let's add that conversion factor. I'll add it right here. The one I use is that 1 meter has 10 to the 9th nanometers. Okay, so if I want meter to cancel, I'm going to put the 1 meter on bottom. 1 times 10 to the 9th nanometer on top. Meters cancel and I'll be left with nanometers. What I got. You guys get that? So you can convert it to scientific notation if you wish. 1.58 times 10 to the fourth nanometers, or you could have said 15,800. Okay. Now let's go the other way. Right? So this time we're going to calculate the frequency given that the wavelength is 235 nanometers.
So we're given a wavelength.
Yes. So you're solving for frequency. Again, you're using this equation. Before I plug anything in, what do I have to do to my wavelength?
Convert it.
Yeah. Then once I have my wavelength in meters, I can take it to that equation. Find frequency, it's going to be speed of light divided by weight. Solved at 1.28 times 10 to the 15th inverse.
And you could also say hertz, right? For the second.
Yes, yes, yes.
Are there any specific cases where we have if they ask for it in hertz or in the other?
Right.
Okay.
I typically myself do inverse seconds. So you'll find that all your math problems in this chapter are simply remembering the formula and plugging in what you have, finding what you don't have. Okay, so that's the first. Now let's do one with energy. So all you're given is wavelength and you're asked to find the energy of the photon. So again, you have two energy equations. One in terms of frequency, one in terms of wavelength. So we're given wavelength, so we're going to use energy equals h times c over lambda. But again, with all of these formulas, wavelength has to be in meters. So let's go ahead and do that. 705 nanometers. .05 times 10 to the negative 7 meters. So now I can plug that in my energy equation. This one, be extra careful when you're entering it in on the calculator. I got 2.82 times 10 to the negative 19th joules. Make sure that you can get that. Let me show you one thing. We'll just use this one. Are we good with this answer right here? All right, I'm going to take it and erase all this. I'm going to do something. So, if this problem had said, what is the energy of 1 mole of these photons? We would have still done everything that we just did. We would have gotten this answer. This answer is okay. When I solved for that, I knew that that was going to be the energy per 1 photon. Okay. But most of the time when I'm working these problems and I get my energy, I leave off this per 1 photon part. It's just kind of understood. So if you ever get a problem and it says, well, what's the energy of 1 mole of these photons? It's the same thing we did in chapter 1. 1 mole has 6.022 times 10 to the 23rd photons. Right. So your photon cancels, and then you'll have joule per 1 mole.
It's like, then you're going to atoms basically, but it's still a photon.
Right. when I solved it for the energy for 1 mole, I got 1.7 times 10 to the 5th joules. So let me do one more like this. Let y'all get that one and try. It says a photon has a frequency 6.5 times 10 to the 9th hertz or inverse seconds. Calculate the energy in joule of 1 mole of photons with this frequency. So the first thing you need to do is you need to find the energy of 1 photon using this energy equation that has frequency in it. I'll get that for 1 photon. Anybody? Okay. Now I'm going to do it to moles. I got a nice clean number for my energy of 1 mole. I got 2.59 joules. All right, so I haven't done any De Broglie, and I don't think I have enough time to do the ones I want to. So I'll do those with the Monday group and then just post them on Moodle. Okay. If I don't finish Monday with all of chapter 2, I'll finish it Tuesday or Wednesday. But as far as studying goes, if you can do the math that I'm doing now, math in chapter 1, I would just be looking over scientists from chapter 1, what they discovered, and then I'd read through my typed notes for chapter 2, where it just talks about black body radiation, threshold of frequency, things like that. I will get y'all a list of all terms and people you should be familiar with. It just won't be today. So, okay, y'all have a good weekend and a good Labor Day. It's not a holiday, but